welcome. In this video we are going to implement the paper that introduced the ELU activation function. So that's now an old paper but very interesting. These are the results we'll get by the end of this video. So we can see the training on validation or loss. First for neural network using the ELU activation function, and another one using the ELU activation function. So on that particular neural network architecture, we can see that the ELU gives much better results. So yeah, we'll dive in the implementation directly. I will put a link to this implementation in the description. So if you find it useful, please leave a star on this repository and leave a thumbs up on this video. And also subscribe for more content related to machine learning. Okay, that being said, let's dive in. So we'll use PyTorch as always in this YouTube channel to implement the papers. Let me know if you're interested in other frameworks like TensorFlow or JAX that is becoming very popular. We'll also use a few other libraries like Seaborn and Matplotlib for plotting the results. We'll use TQDM and Keras, but just for loading the data, not for implementing the machine learning. Okay, so let's start directly by loading the data. The data are encoded, they are discretized with pixels values going from 0 to 255. So the first thing we do, we process the data so that they range between -1 and 1. Which of course will help the neural network quite a lot. Then we can implement the training loop. So that's a very simple training loop. We'll do only supervised learning. So we take as input the model, the optimizer, the loss function. We are doing classification. So we are going to use the negative log likelihood loss. And we take as input the number of epochs that is set to 25 by default. We can create the training loss and validation loss for logging them during training. We can iterate over the number of desired epochs, and then during each epoch we'll iterate over the whole dataset. On a batch is made of a pair of x, which are the inputs of the neural network, and y, the target values. So the first thing we can do is always in supervised learning, we can compute the prediction from the model. So the model is a MLP. So the first thing we do is we reshape the data x. So data x it's a batch of images. So 2D images, and we want to reshape them as a 1D array so that it can be processed by the MLP. We're using MLP because I think this is what they use in the paper for the figure I've shown. Yeah, of course we could also try on CNN. Then once we've computed the log probabilities that the model predicts, we can use the loss function. So we can compare the log probabilities to the target values to compute the negative log likelihood loss. And then we can do a gradient step. So first we set the gradient of the optimizer to 0 to avoid gradient accumulation. Then we backward the loss to compute the gradients, and then we do one gradient step. And then we can, for each batch, we log the batch loss. So we log the loss for each batch, and then we can compute the mean over the batch so that we have a training loss for each epoch. And then we can do the validation. So for each epoch, we do a validation step. So we set the model, the model training to false. So for example, if we are using a dropout, that will deactivate, that will disable dropout. We will not drop neurons. Then we can, again compute the log probabilities and then the loss on the validation data. Once this is done, we can return the training loss on the validation loss. Now we can move on to the interesting part of this video, which is implementing the ELU. So the ELU has one hyperparameter, which is alpha. So we can store this value of alpha, and then we can directly move to implementing the forward pass. So the forward pass we take as input x, and then it's similar to the ELU. So for all the values that are positive, so if x is positive, we apply the unitary transform, the identity transform. So that means we don't need to do anything. But if x is negative, instead of just setting them to 0 like the ELU, we apply another transform so that those values we will apply those values the output will have a small value, but they are not totally killed. So it helps training. We need to be careful not to modify x directly, because x is a pointer. So if you modify x, everywhere in the code x will be modified, and that will lead to very bad results, and this is not the desired behavior. So we need first to clone x so that we have a copy of it, and then we modify the copy and we return the copy. So we only need to modify x where it is negative, so where this condition does not hold, and then we can apply the formula of the ELU described in the paper. And again, be very careful to this dot clone. If you just do y equal to x, y will be a pointer and it will point to the same memory cells as x, and if you modify x, you will modify x as well. So this dot clone is very important. And now that we have the ELU implemented, we can finally put all our pieces together. So first we can create the training dataset on the testing dataset by concatenating pairs of, so for each data point in the training dataset, we create tuple of the input, so the input image on the label for that image, and we feed that to a data loader, well, a PyTorch data loader. We use a batch size of 64, and we shuffle the dataset every epoch. We will try to train our model on the GPU to make it faster. So let's say you don't have a GPU, you can just set CPU there, but yeah, if you don't have a GPU, I would advise to use some cloud computing that are becoming cheaper and cheaper, or just use Google Colab that is free. So first we will implement a model that is using the ELU activation function, so that we can compare it to the model using the ELU activation function, and we use dropout with a probability of dropping neurons with a 50% probability of dropping units. And once we've created our model, we can create our optimizer. We'll use Adam with a learning rate of 1e minus 4, and then we can call the training loop on retrieve the training loss and validation loss and plot them. Once this is done, we can do the same for a model using the ELU activation function. So to do a fair comparison, we use the exact same architecture, but instead of using the ReLU, we use the ELU, the one that we've just implemented. You could also use the ELU implementation from PyTorch by just doing nn.elu, but yeah, I think it's more interesting to implement it ourselves. We could have implemented the ReLU activation function as well. Yeah, so once this is done, we can do the same. So create the optimizer, launch the training loop, and then plot the training loss and validation loss using the ELU activation function. And finally, we can make the plot better, or adding a legend, adding labels, and saving the figure. So that's it. That was a very short implementation, but I think sometimes it's interesting to go back to the basics to really understand them very well, so that when you build a complex architecture, or when you are reusing complex architecture from papers, you really understand why they use one activation function and not another one. Of course, with this architecture, ELU is performing better than ReLU, but on some others, for example, with less, with a fewer dropout probability, ReLU might perform better. So it really depends on your model. But you've seen in the figure, for example, this figure, you can see that we have not marginal, very the performance gain is quite high. So yeah, it's very important to know which one to use, to have at least a bit of intuition behind that. So okay, I really hope you liked this video. If it was, again, please leave a thumbs up and subscribe for more content related to machine learning.